Okay, hi guys. I hope you're all doing well. So, welcome to our lesson today. So, right now, what we're going to focus on is we are going to learn how to find the first derivative or the gradient function by using what are known as the differential or the rules of differentiation. You see, so that's what this lesson is going to be about. But now we're going to demonstrate the rule that applies when you're dealing with the functions uh, whose terms they have a kind of structure which looks like that of a polynomial. That is, we want to learn how to differentiate uh, functions whose terms have this kind of characterization, where a is a real number, like that, and n specifically is a rational number, like that. You see, so that's exactly what we want to look at today: how to find derivatives of functions of that form. So now we are not going to make use of the first principles. So the first principles that we've already discussed, it is the formal way of finding derivatives, but at times it becomes impractical to use, especially when we start involving powers that are rational like that. So we now have to have some tools that one can employ all the time when you want to find a derivative. You see. But before we move on to see how exactly can we differentiate functions of this type, there's just a few things that we want to highlight when it comes to the derivative. You see, so this thing that we refer to as the derivative of a function, it has certain properties that you must be acquainted or know of before we go very far. So one of the things that you should know is that if you want to find the derivative of a constant, so let's say you're asked to find the derivative of alpha, then the derivative of alpha is always equal to 0, as long alpha is just a constant, that is, it's just a real number, and it's purely independent of x, or the variable of differentiation. And also this differential operator, it satisfies the following property. That is, if you want to find the derivative of a sum of two functions called f of x plus g of x, then you should know that this is just the derivative of the sum of the individual functions. You see that? So before we find the derivative, it is good to be equipped with these two properties for the derivative operator. You see, that is, if every time you differentiate a constant, you must always know that the result is a 0. And then the derivative of the sum is always the sum of the derivatives, which means if you are trying to differentiate a sum which has many terms, you can differentiate them individually, one at a time, as you go along the function. You see, so that's what allows us to do when we have these properties. So right now that we know the basic rules that we need, the next thing that we want now is how then can we go about finding the derivative of functions of that form. So in order to give a demo, we are going to look at few examples on how these things work. You see, but before we highlight how it works, it is good to state a rule that is applied to functions like these. You see, so what you should know now is this. You see, so what you should know is that the derivative of a function like this one, ax to n, is actually given by an x to n minus 1, like that. So this is actually a rule that summarizes the whole process of how to differentiate functions of that form. So if you pay attention to that, it might take you quite some time to actually get the message as to what exactly are we being taught there, because this is not exactly a formula that you have to use to differentiate things, but it's more like an algorithm, a set of instruction written in mathematical form. So you just have to extract out the recipe for finding derivatives, and then you just leave that thing alone. So that's what we're going to demonstrate now by looking first at basic examples, and then we just do a few tricky ones. So first question that we're going to look at is as follows. So given that y is the function x to the power 10 or 3x to the power 10, find dy dx. So if you're given something like that and then they say find dy dx, how can we go about finding dy dx? So to find an answer to this one, then we proceed as follows. So if y is equals to 3x10, how do you find the derivative? So every time when you're given a function like this one, and you want to find dy dx, this is how you go about it. The first thing that you do is you take the power that is given and you multiply the coefficient of that term. So that's the instruction number one that is incorporated in that definition. So every time when you want to differentiate any function which has this kind of structure, you start first by taking the power and multiplying the coefficient. So when you take the power and multiply the coefficient, you will get 30. And then after doing that, you bring the variable that carries the power next to that. And then now the power that is there is also brought forward. But when you are bringing it, you first have to deduct 1 from it. So when you deduct 1 from it, you get 9. So that's why you see here, if you go back to the formula, there is an n minus 1, which shows you that the power always has to decrease by 1 when the process is completely done. So that's exactly what is going on there. So these are the steps that are summarized in that whole thing, you see. But to get this, let's look at more examples, because one example cannot do justice. So let's look at another one. So another one you can be given, they can say given maybe a function f of x, which is defined as cube root of x plus half x to minus 1/3, find dy dx. So now we're looking at least some problems that will require us to think a bit, but let me change a bit here. Let me actually put half there. And then let's see what happens. So now again, we want to find the derivative here in this problem. So this is how we proceed, you see. So now, if we look first, the function f of x given, it has its term appearing in the structures that are not exactly a resemblance of what we've just learned. So every time before you apply a rule to differentiate something, you must always first look at, pay attention to the structure of your terms. Do they resemble exactly what you have in your definition? So if you look at the second term in the function, it is perfectly fine because it has the structure that we need, which is the ax to n structure. But the first one has a problem. So to do that, what we do is we have to recall what we know from the definition. So we know that cube root of x by definition simply means x to the power 1/3. Then we bring that other half and we get half x to minus half. Then now everything, when it's okay, now we can start differentiation. So what is f prime of x? So the first thing is, as usual, we take first the power and multiply the coefficient. So we take the power first, you multiply the coefficient, but since there is no coefficient, it's 1, so we multiply, we just get 1/3. Then you bring your letter x here, but after bringing x, the power also is taken here, is transposed as well. But when the power is being transported to the answer, 1 has to be deducted from it. So which means we have to take 1/3 and then you subtract 1, and this will give you negative 2/3. Then again here, same thing again. I take my power, I multiply coefficient. So it means I will have a half multiplied by a negative half, which will give me a negative quarter. Then I bring x. Then from this negative half that is here, I transpose it, but as I'm transposing, I subtract 1 from that. So when I subtract 1 from that, I get what? So I'll get minus 3/2. So that's what happens here. So that becomes your final solution. So this is how you get to differentiate functions of this structure. But then to do one more last example again, to practice more of this, let's look at the following problem again. So you can be given the following expression. So given that y is equals to x to power 4 plus 3x to minus 2 plus 7 over x 6, find dy dx. So you can be given something like that, and then they say find dy dx. So how can we answer this problem? So to answer this problem first, we can see that what we have doesn't really look the way we want it. So what we have to do is to first fix this to align to the structure that we want. So one of the things that we know is that every time when this is true, then we know that actually this implies that x4 over x6 plus 3x minus 2 over x6 plus 7 over x6 is also true. You see that? But when we simplify this by laws of exponents, then we see that in the first I get x minus 2, then I get 3x, then to minus 8, then I just get 7x to minus 6, like that. So now things are appearing in the normal structure that we need. So therefore now what is dy dx? So to find dy dx, now I do the rule, I bring down the power first, minus 2, then I put x and decrease it by 1, I get that. Then I multiply the bottom, I get minus 24. Take x, reduce the power by 1, I get negative 9. Then again, I multiply 7 by 6, I get minus 42. Bring down the power, I reduce it by 1, I get minus 7. So this gives us that. So if you want, you can write your answer as minus 2 over x cubed minus 24 over x9 minus 42 over x7. Then that concludes everything. So this is how then you find the gradient functions of functions that have what we call a polynomial structure. So you just do the differentiation in 3 steps. You bring down the power to multiply the exponent, bring x again, take the power of x, reduce it by 1. So it's just a simple 3-step process like that. And then it's done. So yeah, that's it. So thanks for watching. So see you on our next lesson where we're going to learn how to differentiate a different type of functions other than the one that we've seen here. So goodbye.